Good day everyone, we are Group 5 and we are here to discuss about topographic surveys. Starting off, we have Don Bensig.
So for our first discussion, we're going to be talking about the representation of a relief. So what are so before talking about before talking about topographic surveys, first we have to ask ourselves what are topographic maps. These maps would show you vertical data such as elevation and the height that would represent the actual elevation or the 3 or the 2D representation of of a certain place. So, topographic maps show the configuration or shape and roughness of the ground. This roughness is commonly referred to as a relief. Throughout time, depicted of the relief of a parcel of land changes as people began to develop other types of topographic maps. Topographic surveys, the, these involve all procedures, equipments, and methods necessary to capture both horizontal and vertical data of points on the ground strategically chosen to depict terrain. Modern topographic maps have points called contours, which will be further discussed by my other groupmates. These elevations on these lines are based on known assumed datum. So in the next couple of slides, I'm going to be showing the different types of topographic maps. Starting off with our first, which is called sugar loaves. These are these are idealized depiction from a side or oblique view. The only form of topography on early maps pre 1700 is due to the lack of detailed surveying. It gives the locations of mountains or hills but does not give the precise size or the precise elevation of that said mountain or hill. The second one are called hatchers. Ha- Hatchering use lines of varying width and length to depict slope steepness drawn in direction of the slope. Initially, unsurveyed and little better than sugar loaves, the first form knowing giving general location of mountain ranges are referred to as hairy caterpillars. Hatchers are not often used except when the scale of the map is too small. So these are the hatchers are more of a slightly surveyed area and gives you a little more of an idea on what the actual size of the place is. The disadvantages of these types of maps, however, is the lack of information and the difficulty in distinguishing the direction of the slope. It it is also not very effective in mountainous terrains. It is a map that is time consuming to produce and obscures other information. The only advantage that you could get out of these maps is that they may show minor but important details, other but it is otherwise lost on a contour map with the contour intervals. Next, we have contours. As I said a while ago, this will be further explained by my group members, but in order for them to but I'll just give a few details so that it could support their further discussion later. So, contours came initially from the need to know the exact depths in water and were generated from a series of depths or soundings. The first contours in the late 1900s were on navigation charts as isobaths. They are essentially an isorhythm or an isopleth. They are lines drawn on a map through all points having the same numerical value, as of a population figure or geographic measurement. The contours basically came from the need to know the exact depths in water and were generated from a series of depths or soundings. The first contour in the late 1900s were on navigation charts such as isobaths. Next up, we have isometric tints. Isometric tints are the addition of color to elevation levels. Uh, it was first tried as early as 1830. Color schemes require graduation, logical sequence, realistic colors, with the darkest still able to bear readable text. The disadvantages of isometric tints is that it doesn't really add new information. You're just basically giving color to the different depths available on that map. And differential contrast between tints and other elements, dubious associations. Uh, Others may think that the green part is actually a forest, where in reality they they show the difference in depth compared to the others where it is marked orange or red. The advantages, however, it adds imageability. It is easily applied and understood. Just like you could see on the right picture, you could easily tell where are the low depths and the high depths of that certain map. Next up, we have shaded reliefs or hill shading. This involves the addition of shadows to give the illusion of depth, assuming a theoretical northwest light source or at 45 degrees elevation. Introduced in the 1900s but became more widespread after the 1960s with improved printing technology and users' needs. It has become much more common with automation. The the advantages of shade of hill shading is that it is highly imageable, continuous in appearance as in reality, and can show greater detail and character of the landscape. However, the disadvantages is that it manually required artistic creation with pencil or airbrush. It was costly and often poorly rendered. And it is also highly inefficient as it would require more time to create these types of maps. And next up, we have the block perspective diagrams. These are the maps that would actually show the 3D representation of that certain place. The disadvantages of this is that it is the most time consuming map to produce with no consistent linear scale. But we are also basing this, the most time consuming to produce, we are basing that on the era that before computers were invented. The advantages on this is that it is the most imageable portrayal of a landscape. It is in 3D. It can accurately depict the it can accurately portray the difference in height of certain landscapes. Next, we have the Tanaka relief or contours. This technique of applying a northwest light source to a contoured landscape was first tried in 1850, but printing methods then could not handle the gray backgrounds. It was pioneered from the 1950s by Kitiro Tanaka, who produced some exquisite examples using the theory of application of shading principles of contouring. And
Thank you, Don. Now, we move on to the next part of our report, which is all about contours. Contours is what makes a topographic map different than other maps due to it being lines that represent elevations. Next slide, please. In this part of the report, we will be tackling about the different types of contours, the contour interval, and the characteristics of contours. Next slide, please. So, the first section, or the first part of the report, is the different types of contours. Next slide, please. So, there are 5 types of contours, wherein each of these contours have different purposes in a topographic map. First is the index contours. Second, the intermediate contours. Third, the supplemental contours. Fourth, the depression contours. And fifth, the approximate contours. I will be discussing each of them. The first type is the index contours. These are contours where it is displayed as heavy or bold lines with a number along its course, which symbolizes an elevation designation, or the elevation. It usually appears on regular intervals, normally shown on every fifth contour. Next slide, please. The second type is the intermediate contours. These are contour lines in between the index contours. and they follow the contour interval used in the map. These lines are finer or thinner than the index contours, and their elevations are not given unlike the index contours. A side note to be remembered is when intermediate contours are too close to one another, it is suggested not to draw those short distance lines. Next slide, please. So, in this picture, we can see here the differences between the index contours and the intermediate contours. As you can see here in the picture, the index contours contains the elevation 11,000, 10,800, and 10,600. And in between the index contours, those are the intermediate contours. And the number of the intermediate contours depend on the contour interval. Next slide, please. The next type of contour is the supplemental contours. These are contour lines that is used to display the elevation when there is an area in the map where there is little to no elevation change, such as a flat terrain, or if you can see in a topographic map, there is a wide contour spacing. This can be symbolized as dashed lines or lines of dots. These lines are usually drawn one half of the contour interval used. Next slide, please. The next type of contour line is the depression contours. These are lines that symbolize spots in a topographic map that are lower than the surrounding elevations, such as holes, excavations, and downhills where the contour closes. These lines can be identified as ticks perpendicular to the contour line. As you can see in the picture on the right, we can see that the depression contour appears when there is an area in the map which is lower than surrounding elevation, and it can be symbolized as you can see in the top left corner in the right image. It is symbolized as ticks perpendicular to the contour line. And it is also noted that the depression contour, as you go to the center, the elevation lowers. Next slide, please. So, last but not the least, the next contour line is the approximate contours, which are lines that are approximately determined. These are lines that are drawn or plotted based on the educated guess of the surveyor's perspective. This line is usually used in areas where it can be difficult to access and measure their elevations. So, the approximate contours can usually be used when there's a cloud blocking the bird's eye view of one map. What a surveyor will do, he will approximate where is the trend or where is the path of that contour line. Next slide, please. So the second section of my report is we will be tackling about the contour intervals. We will also be tackling about how it can be determined or how it can be selected. Next slide, please. So we have to ask the question, what is contour interval? Next slide, please. So a contoured interval is the constant vertical distances or the difference in elevation between the contour lines. The contour interval can depend on the height of the areas and features present nearby. Small, interval, Small intervals are used for areas with low differences in elevation, while larger intervals are used for areas with higher differences in elevation. Next slide, please. So we discussed about what is a contour interval. Next, we need to know how to determine a contour interval. Next slide, please. As you can see from here in this picture, there's a topographic map, or this is just part of a topographic map which shows different contours. So as you can see from here, for us to determine the contour interval, we need to use this formula in determining the approximate contour interval, which is formulated by the next index elevation minus the previous index elevation divided by the number of lines in between, including the next index contour. So in this picture, I used 400 as my next index elevation, and previous to 400, which is 200. So if I count the lines between 200 to 400, which is 1, 2, 3, 4, 5, which is 5. So if I use this given data and I inputted it in my formula, I can get 400, which is the next index elevation, minus 200 over 5. If we calculate, we can get a 40 feet interval or 40 unit interval. Next slide, please. Another way of determining the contour interval can depend on the scale of the map and the terrain. So as you can see from here, from the scale of the map from 1 over 500 to 1 over 2,000, 250,000, as the scale gets smaller, the interval gets bigger. So in the yellow table in the right, there's a types of topographic map, which is the large scale, intermediate scale, and small scale, and it features the nature of the terrain. So usually the contour interval will also depend on the situation or the scenario surrounding the large scale, the intermediate scale, and the small scale topographic map, or the surrounding area or the surrounding landforms in those maps. Next slide, please. So now we move on to the selection of the contour interval. Next slide, please. So here are the factors in selecting a contour interval: the relative cost, purpose of the map, nature of the terrain, and scale of the map. Next slide, please. One of the factors One of the factors in selecting a contour interval is the relative cost, wherein the expenses of conducting the survey and fieldwork is considered. It is also noted, as the map contains smaller intervals, it creates more contour lines, which increases the cost of the map due to more fieldworks to be done. Next slide, please. The second factor is the second factor is the purpose of the map. As mentioned in the previous slide, different terrains and situations require different contour intervals. For precise constructions or projects, there's a need for lesser contour interval. The third factor is the nature of the terrain. This means the surrounding environment can dictate on what contour interval is to be used. As such, with the yellow table I have shown before. An example for this is for rugged terrain, there's a need to use for a rugged terrain, there's a need to use a larger interval, while a flat ground or flatter ground, there's a need to use for a smaller interval or a smaller contour interval. Next slide, please. This is the last factor of in selecting a contour interval, which is the scale of the map. The last factor, as mentioned in the previous slide, there's an interrelation between the scale of the map and the contour interval. Usually, the smaller the scale, the bigger the interval, as what I have mentioned before. Next slide, please. And now we move on to the final section of my report, my part of my report, which is the characteristics of contours. We have discussed previously the types of contour lines and the contour interval. Now, we move on to discuss the features and parts of the contours that we need to know and be aware of to further increase our knowledge and capabilities in utilizing the contour lines to its fullest potential. Next slide, please. The first characteristic of a contour line is that it must close, either inside the map or outside the map. A contour that closes within the map usually pertains to a depression contour or a summit. Second, as related to the first characteristic, a concentric closed contours with the elevation decreasing as it moves towards the center may indicate a depression. Decreasing as it moves toward the center may indicate a depression or pond, as you can see in the bottom left picture. And concentric closed contours with the elevation increasing towards the center may indicate the presence of hills or landforms that rise, such as a plateau, volcano, and mountain, such as the picture in the lower right, as you can see from here. Next slide, please. Another characteristics of contour is that widely spaced contours pertains to flat surfaces, while closely spaced contours pertain to steep elevations, and equally spaced contours pertain to uniform slope terrain. So, all in all, this means that the horizontal distance between any two contour lines indicates the amount of slope and varies inversely on the amount of slope. This means as it gets closer, the elevation gets steeper, and as it gets further, the elevation gets flatter. Next slide, please. Fourth is irregular contours. It indicates uneven surfaces which can be rough and rugged terrain. Fifth is that all points within the course of a contour pertains to the same elevation. An example of this is the index contour, wherein the number in the index contour pertains to to all the elevation in that course or in that index contour. Next slide, please. Contours that overlap. Contours with different elevations cannot overlap on one another. But if this happens in a topographic map, this can pertain to a presence of overhanging cliffs or cave, as you can see from the picture in the right, where there is an overlap between the 250 elevation and the 200 elevation, which can symbolize or which can mean there is an overhanging cliff. The seventh is the relationship between contours and building. Contours does not pass through infrastructures or buildings built within varying elevations. So, if you put it in a map, previous slide please. So, if you put it in a map, if you put a building in between different elevations, the elevations does not pass through the building. So, this can be there's a building in my hometown, in my home city, which is Ormoc City, which is called OSPA FMC. So OSPA is the hospital OSPA is located on an elevation. So if we try to put this hospital in a topographic map, we can show it can have a relationship with the right picture, with the picture on the right, which can be which is which is where the topographic lines or the contour lines does not pass through the building, which is the blue figure. Next slide, please. So the eighth is the contour lines with U shape. So contour lines with U shape with convexity towards the lower ground, it indicates a ridge, and contours cross curves and a crowned sloping street in typical U-shaped curves. So those are the description of contour lines if they appear with a U shape. So the contour lines which appear with a V shape, they have a convexity towards the higher ground, which can indicate a valley. And contours cross streams in a V pattern pointing upward. So the second statement that I have mentioned, which is the contours cross streams in a V pattern pointing upward, is just a description of the contour lines with the V shape and how it can be identified as a valley. Next slide, please. So we will be now moving on to 5.3, the topographic mapping, which will be presented by Joseph Santolaha and Aaron Makinano. Thank you.
For the next topic, we are going to discuss about topographic mapping, obtaining contour lines by checkerboard method. Next slide, please. Mapping surveys. These are made to determine to locate natural and cultural features on the Earth's surface. And these these features are made to define the configuration on that particular surface. Examples of natural features are vegetation, rivers, lakes, oceans. On the flip side, examples of cultural features are roads, buildings, urban development, boundaries, railways, and power transmission lines. Next slide, please. Map scale. Next slide, please. Map scale is the ratio of the length of an object or feature on a map to the true length of the object or feature. These are given in three ways. First off is the ratio of representative fraction, or 1 is to 2000 or 1 over 2000. Second is equivalence, wherein 1 inch of a ruler is equal to 200 feet when measuring a topographic map using a ruler or any measuring device. And lastly, we have graphically, using either a bar scale or labeled grid lines that are spaced. Next slide, please. Here we have an example of a bar scale, and the next slide. Next slide, please. We have a example of a labeled grid lines. Next slide, please. Contours. Next slide, please. Contours are imaginary level lines that connect points of equal elevation. Using contour lines is the most common method of representing the topography of an area, and these cannot be seen in nature. Next slide, please. The elevation difference between adjacent contours is called contour interval. And contour intervals depend on the map's purpose and scale. Next slide, please. Here we have a photo containing contour lines. We can see in the photo, we can see the contour intervals as well as the index lines, the lines that are measured that was mentioned earlier by Julius. Next slide, please. On maps, contours represent the planimetric locations of the traces of level surfaces for different elevations. On the photo, labeled small letter A, we have the plan view of contour lines. B, we have the profile view, and on B and C, we have the profile views. Next slide, please. Characteristics of contours. Next slide, please. I would mostly be reading on the slide since most of these characteristics are self-explanatory or are simple to understand. So starting off, characteristics of contours. The first characteristic is closely spaced contours indicate steep slopes. Second, widely spaced contours indicate moderate slopes. And contours should be labeled with an elevation value. Contours are not shown going through buildings, and contour lines do not cross each other. Depressions, craters, or sinkholes look alike in the map. Note the contour value to distinguish the terrain. Important points can be further defined by including a spot elevation. A spot elevation is a point on a map that identifies the height above mean sea level. And the spot elevation tells you the actual elevation of a particular point, both existing and proposed, which can be used for planning purposes and for creating 3D models. Contour lines tend to be parallel to each other on uniform slopes. And lastly, contour lines must close on themselves either on or off a map. Next slide, please. Contours are perpendicular to the direction of maximum slope. The slope between adjacent contour lines is assumed to be uniform. And the distance between contours indicates the steepness of the slope. As mentioned earlier, if they are further apart, these are gentle slopes. If they are closer, they are steeper. And if they are even and parallel, these are uniform slopes. Irregular contours indicate a rough and rugged terrain. Smooth lines are more uniformly rolling terrain, and concentric closed contours that increase in elevation represent hills. Contours of different elevations never meet except on a vertical surface, such as a wall, cliff, or natural bridge. And a contour cannot branch into two contours of the same elevation. And lastly, contour lines crossing a stream point upstream and form V's. Next slide, please. Here we have a formula. Here we have the formula of the in calculating the gradient of a contour, wherein we divide the vertical interval with the horizontal interval. With the, in okay in show in the picture shown below, we have a gradient along AC where the vertical interval is 10 and the horizontal equivalent is 100. If you divide 10 with 100, you get 1 in 10. And with the gradient along DE, the vertical interval is 10 and the horizontal equivalent is 30. After dividing, you get 1 in 3. Next slide, please. Here we have the different types of slow we have different types of slow contours. First off, we have the regular gradient, the concave slope and the convex slope. Next slide, please. And if you can see this in your topographic maps, the river valley V points upstream, and if the V points downhill, it is forming a nose. Next slide, please. Here we have the rules when viewing topographic maps. The first rule, which is the rule of V's. Sharp pointed V's usually are in stream valleys, with the drainage channel passing through the point of the V, and with the V pointing upstream. Rule of O's. Closed loops are normally uphill on the side and downhill on the outside, and the innermost loop is the highest area or the summit, or usually the summit. Imagine a cake, or imagine a hill which is sliced by a really big knife. That's how you view rule of O's. and its spacing of contours. Close contours indicate a steep slope, distant contours a shallow slope, and two or more contour lines merging indicates a cliff. Next slide, please. Here we have the additional examples for rule of V's and rule of O's. Where in the photo below rule of V's, we can see the V that indicates a stream. And additional example for rule of O's, we can see the contours on a hill. Next slide, please. And for more important tips and identifying contours, the selection of a contour is crucial in doing topographic surveys. The contour interval should be small enough to give the desired topographic detail while remaining economic. And lastly, usually every fifth contour line is shown in a heavy, wider line called the index line. These lines are the only ones labeled since it is impractical to mark the elevation of every contour line on the map. Next slide, please.
Locating contours. Next slide, please. Here are the few methods of locating contours. Next slide, please. So one of the method is direct method. This method requires the contours to be located directly traced out in the field by locating and marking a number of points on each contour. So this method is accurate, but it's also tedious since you'd have to uh you'd be wasting time searching points with the same elevation for a contour. Next slide, please. The next one is indirect method. Unlike the direct method, this one does not follow the contour line, but instead uh, uses spot levels to on a series of lines laid out in the area. This method is also cheaper, but is also not accurate, so it is advised to be used on a large-scale survey since accuracy is not the main concern. Next slide, please. Coordinate squares. According to the type of ground and the contour interval, the entire area is split in a number of squares. When necessary, measurement from corners can be used to pinpoint the essential points within the squares. The decreased level of corners are recorded in the plan and the squares are plotted. Next slide, please. So construction of contours. Here, we plot points contours based on the uh, points that are made on a on the terrain. Measuring the elevation of the points are first step in the process of making a contour map. The use of marks on the points to be measured will make the work more efficient. By using the available instruments, one can establish the location of these points. Next slide, please. So here is a sample map to be plotted on a contour map. It has a it already has its given, and the interval to be done is 5 feet interval on the contour map and a rectangular grid with a dimension of 80 feet north and 100 feet east. Next slide, please. A basic method for estimating contour is applied to each grid cell. In order to find the location of the desired contour interval, use linear interpolation. Consider the contour interval of 5 feet in finding the contour interval. Next slide, please. Check if a contour interval exists between nodes of a grid cell and estimate the location of a contour interval along the line, like that 100 and 105, and apply linear interpolation on each side to locate the contour interval. And the next slide is to be explained by Julius Ngo.
Thank you, Aaron. Now we move on to the construction of contours using the checkerboard method, as previously stated by Aaron. As if we look at the left picture, here there is a need for us to look at the top edge of the grid cell. So as you can see here in the top edge of the green cell, it has four corners, which signifies the elevation on each grid, or the elevation on each corner, which is 98, 102, 101, and 108. But first, we need to focus on the upper edge or the top edge of that grid, which is from 98 to 102. As previously stated by Aaron, there is a need for us to estimate on where will be the contour interval, which has a 5 feet contour interval. So first, we start off with 100. So if we estimate where will 100 be, it will be in between 98 and 102 or in the middle part. So after estimating where will be the 100, we will be now solving for the horizontal distance from 100 from the 100 checkpoint to the 98 checkpoint using the slope intercept form or the slope interpolation form or the linear interpolation form. You'll be using the slope intercept form, which is y is equal to slope times x plus b, which is the y-intercept. So if we substitute all the values for the slope, we find the slope by 102 minus 98, 102 which is the top right corner, and minusing it to the top left most corner, which is 98, and we divided where we divided it by the 100 feet east, we can get the slope, which is 4 out of 100. And for the intercept, we will use 98, which is the top leftmost part of the grid. So if we equate it in slope intercept form, which is y is equal to mx plus b, if we equate it, we will get 100 is equal to 4 over 100x plus 98. So for us to determine distance from 98 to 100 horizontally, we will need to solve for x. So if we solve for x, we can get 2 times 100 over 4, which will be 50 feet. Meaning from the 100 checkpoint to the 98 checkpoint, there is 50 feet of space in between or 50 feet of horizontal distance in between. So in the right image, which states at we need to look at the bottom edge of the grid cell, we'll be focusing from 101 to 108. So we will be using 105 because this is a 5 feet interval, which is 5 more than 100. Now, we'll be solving it the same way as we solve for the top edge of the grid cell by finding the slope, finding the intercept, and finding the horizontal distance in between 105 to 101, which is the bottom left corner, which is 101, bottom left corner of the grid. So if we solve for the slope of 108, which is the bottom right, minus, and we subtract it with the bottom left, which is 101, if we solve for the slope, 108 minus 101 over 100 feet east, and we use the intercept of 101 or our basis, the intercept which is 101, which is the bottom left corner of the grid, and we put all those values inside a slope intercept form, we can get 105 is equal to 7 over 100 101. So we will get 4 times 100 over 7, which will be 57 feet. So 57 feet is the horizontal distance between the 101 grid corner to the 105 contour interval. Next slide, please. Now we move on to the left and right edges. For solving the left and right edges, instead of using the 100 feet east, we will be using the 80 feet north for the slope. But the concept will be still the same in calculating for the slope and the intercept in terms of using the slope intercept form. So if we look at the left side, which states that we need to focus on the left edge of the grid cell, the top we will be focusing on the left edge of the grid cell. The top left indicates 98 and bottom left indicates 101. So if we equate for the slope 108 minus 98 over 80 feet north, we will get 3 out of 80. And if we get the basis or the distance we need to find, which is 98, we will be using this data in the slope. We will be substituting this data in the slope intercept form, which is 100 is equal to 3 over 80 x plus 98. So if we equate for x, we get 2 times 80 over 30, which is 53 feet. So that will be the horizontal distance from the 98 feet elevation to the 100 feet elevation on the left edge of the grid cell. The same will be said in the right image, which focuses on the right edge of the grid cell. So for the right edge of the grid cell, we will also be using 105 because this will be the contour because this follows the 5 feet contour interval from 105 to 100 to 105. Now, equate if we equate for the slope and the intercept, get 102 for the intercept because it is the top right corner, top right corner of the grid cell, and we will be calculating for the slope, which is calculated from the bottom left corner minus the top right corner over the 80 feet north, which will be calculated as 6 over 80. So if we substitute all these values that we have found out to the slope intercept form, which is y is equal to mx plus b, we get 105 is equal to 6 over 80x plus 102. In order for us to find the horizontal distance from the 102 elevation to the 105 elevation, there is a need for us to solve for x, which is 3 times 80 over 6, which is equal to 40 feet. Now, next slide, please. Now, as we found out the location of the horizontal distance and the approximation of the location of contour intervals, there is a need for us to connect all points that we have found out of equal contour intervals. We need to connect them, and we have to do the same thing to the other grids. So if we do the same thing with the other grids, next picture, please. Next slide, please. If we do the same thing to all of the grids, we will get this picture, which is stated here. It is the repeating the linear interpolation for each of the remaining grid cell. It gives us this image, wherein, as you can see from here, as the various points connect to one another, this signifies one contour line. As you can see from here, from 100, it is in between 98 and 101, and in between 98 and 102. This gives us a consistent contour line of 100. In the second line, it gives us a consistent contour line of 105 from the left to the right. And here in the bottom part, over at A, it gives us a 110 contour interval, which will be consistent through all of the grids in the map. Also here, if you calculate for 115, it will also be shown here, which is a closed interval. And if we solve for 110 again, because it shows a decreasing elevation, it can be shown here at the bottom right corner of this grid. Next slide, please. Next slide, please. So that will be all for our report. Thank you, Miss, for listening to us, and thank you, blockmates, for listening to us. And thank you, goodbye, and God bless. Sponsored by Netflix. Thank you.